You have assignments for me. Ridiculous stuff. So the consequences of our properties on relations are most manifest when we look at something called an equivalence relation. And I want an equivalence relation to be defined as any relation on a set, so that's from A to A, that is all three, reflexive, symmetric, and transitive. So what kind of things have these properties? Pick an alphabet. I don't care if you use the English alphabet, the Cyrillic alphabet, the Elvish alphabet, it doesn't matter. Within an alphabet, we're going to look at strings. So words, they don't have to make sense. Zizzy makes a perfectly good string of English letters. I don't know what the hell it means. But I can define a relation A is related to B if A and B are the same length, the number of characters used. Okay, let's check all three properties. Is this reflexive? Why, Royal? Right. The length of this string is the same as the length of this string. Whatever that number is, I'm not changing strings, it's the same number. How about symmetry? Is this relation symmetric? Let's go through the definition of what symmetric means. It means if A is related to B, then B is related to A. So let's start by supposing that A is related to B. What does that mean for this particular relation? It means that the length of A is equal to the length of B. Well, that's an equal sign, right? So it doesn't matter what's on which side of an equal sign. And now that those two are reversed, these two are reversed. If A and B have the same length, then B and A have the same length. Is this transitive? Again, we can write out an argument. It's a direct proof, right? That's the definition for transitive. If A is related to B, then what do we know about the lengths? What is equal? Careful, careful. A and B could be any strings. Do they have to be the same string? But they have to have the same, somebody said it over here, the same length. If length of A is equal to length of B, and length of B is equal to length of C, then the length of A is equal to the length of C. It makes perfect sense, right? That's exactly what we need to write out. A related to B means length of A is the same as length of B. B related to C means that the length of B is the same as the length of C. Put those together and we get that the length of A is equal to the length of C. Therefore, A is related to C exactly as we wanted. Now, this sounds kind of bonkers. Me to be talking about lengths of strings, but in one sense, every time I code, when I'm figuring out how to put a field in place, I need to know how big that field's going to be. Does anybody here have a friend or a relative named Christopher? I have a friend named Christopher who, for my entire childhood, I did not know he had an R on the end of his name. CHRISTOPHE. Because the stupid field in the school roster for first name was 10 bits long. His name is 11 letters. I never knew he had an R on the end of his name until I saw something that he wrote. Every form he got from school said Christophe. The string. But we've already done this. We've already done equivalence relations, but we didn't think of them that way. A is equivalent to B mod M. I even used the freaking word. How do I know when two integers are equivalent mod M? Chapter 4. I didn't hallucinate you all being here. You took the exam that this was on. What's that mean? A is congruent to B mod M. A is equivalent to B mod M. How do I know if two numbers are equivalent? And checking for what? That's exactly the definition. I can write it as A minus B or B minus A, it doesn't matter. Is this reflexive? Got to check, right? Well, that's only going to be true if m divides this difference. So I want to know if m divides a minus a. But what's a minus a? And 0 can be divided by any number. The quotient is 0 and the remainder is 0. It worked. How about symmetric? Kind of gave it away earlier when I said it depended on the way I wrote this. But having chosen b minus a, I need to prove that if a is related to b, then b is related to a. That's our definition. If I tell you that a is congruent to b mod m, that means that m divides b minus a. How do I show the other way around? Right, but how do I get there from here? How do I know that sentence is true? Well, if m divides b minus a, that means that b minus a is something times m, where k is an integer, right? That's what it means to divide evenly. Now I need to look at a minus b, because that's going to reverse the position of all of these letters. So what do I know about a minus b? Say that again. It's negative. It's the negative of b minus a. And that means it's negative km. Well, let's put the parentheses in a different place. That's integer times m, isn't it? K was an integer, so negative k is also an integer. And that means that m divides a minus b. And that means that b is congruent to a mod m. So it is true, but I don't get it for free. I have to work for it. I have to go back to the definition of what this relation means. The same thing is true about transitive. How do I end up with A is congruent to C? Let's write out our rearrangements here, right? This means that M divides B minus A. This means that M divides C minus B. Since I want A congruent to C, what's the end statement I want? And we'll look at M dividing what? C minus A. Well, let me take a look at C minus A. Wait a minute. C minus A is C minus B plus B minus A, isn't it? I subtracted B and I added B. This is a calculus trick. I add 0, I multiply by 1. I can't tell you the number of times I said that back when we were doing limits. It's been at least a semester. Wait a minute. M divides this. M divides this. That means that this is a sum of integers times M. I don't even have to have relations on a set of numbers or a set of letters. I can do people. How many of you are registered for classes next semester? When did you register? What day did you register for classes? There was an email that came out, right, from the registrar's office. And it said that this was the date you were allowed to register on, right? And it was based on what? In what class? What do you mean by that? My class, my year, which is based off of the number of credits I earned. So, I don't remember what the date was, but there was a date that it said seniors, as in people who have 90 or more credits. And then we had juniors, which had 60 to 89 credits. And then we had sophomores, which had 30 to 59. And then we had freshmen, which had 0 to 29. I can now divide the entire student body up based on when they registered. I'm going to make an assumption for the moment. These people registered on Monday, these on Tuesday, these on Wednesday, these on Thursday. Registration eligibility date is a relation on the student body at Seton Hill. Here's my set. I claim this is an equivalence relation. Is it reflexive? Please notice there's no math to do now. Is this a reflexive relation? Do you register on the same day as you? Every person is eligible to register on the day they are eligible to register. That's what reflexive means. A is related to A. A is related to B, then B is related to A. That's symmetry. If person 1 can register on the same day as person 2, then person 2 can register on the same day as person 1. If person 1 and 2 can register, and 2 and 3, do 1 and 3 get to register on the same day? That's transitive. So this is an equivalence relation, but I didn't do any math. I just described the relationship and looked at the process. Questions? Royal, you used a wonderful word here. You said class, right? The collection of things that are equivalent to a given element of my set is called the equivalence class of that element. Formally, it would look like this. Let me go back to our examples for a second. First example was the length of strings, right? A string of letters in the English alphabet. There's a string of letters in the English alphabet. I would like to know, under our relation, which I called length, what is the class of things related to the string? Hello. My equivalence relation is length. So the set of things in the strings of English letters that are equivalent to this are any other string whose length is the same. The equivalence set, the equivalent class, is the set of all 5-letter strings. There you go. There are some examples of 5-letter strings. Anything whose length matches the word we started with are equivalent under the relation L. And Royal, this is why we call them classes of students. Any student who has between 0 and 29 credits is in the freshman class, because that was our equivalence relation right here. Anyone with 60 to 89 credits is in the junior class. It doesn't say anything about when you're going to graduate. It doesn't say anything about how many years it took you to get there. I know some part-time students who would have taken 10 years to become a sophomore. It doesn't matter. But what we create is an equivalence grouping, a class of elements. Somebody pick an integer. A moderately small one. 7. Okay. We already decided that modulus a number, A is congruent to B, mod 7, because now you just picked 7. Let's look at the classes here. Pick a number other than 7. I'm sorry? 11. I would like to know what things are equivalent to 11 mod 7. In other words, I want you to solve that. That's infinitely many numbers, right? There are a whole bunch of numbers that are equivalent to 11, but I absolutely know that 11 is one of them. So is 4. Why? 11 minus 7. The difference is divisible by 7, which means I could go the other way as well, right? And I could add more and more 7s. And I could subtract more and more 7s. And all of those are in the class that goes with 7. Goes with 11 mod 7. There's another way to write this set, though, right? I could think of taking any number and adding some number of 7s to it. If we started with 4, we could go add 1 7, add 2 7s, 3 7s, 4 7s, subtract a 7. These are all of the form 4 plus a multiple of 7. Which is how we thought about mods in the first place. Like, they were remainders. I'm saying that that entire set of numbers, every one of these, has a remainder of 4 when you divide by 7. Which means another thing I could call this is not just the class of 11, I could also call this the class of 4. I could call it the class of 25 if you wanted, or the class of 103. I just need whatever the appropriate multiple of, just realized 103 is the wrong one. 91, 14, 105, 109. How many other classes are there in this relation? Remember, the set of integers is an infinite set. But this class is an infinite class. That's one piece of the integers. How many other pieces are there? Somebody pick a number that's not on the screen. 12. Let's build the equivalence class for 12. I just added 7s going to the right and subtracted 7s going to the left. So here is a different class. Please notice something else. How many elements are in both of these classes? Say again? None. Because if you're in the top class, your remainder is 4. If you're in the bottom class, your remainder is 5. Can you have a remainder of 4 and 5 when you divide by 7 at the same time? How many remainders are possible when you divide by 7? Zero, 1, 2, 3, 4, 5, 6. A total of 7 distinct, separate classes. If you're looking at things that are equivalent, and you have 2 piles, there are only 2 choices. They either have no intersection at all, or if they even have 1 element in common, they must be exactly the same. What? Oh, wait a minute. If I have something in here, they're all equivalent to some x, yes? But if that x is also in here, then everything in here is equivalent to the same x. That means everything in the first set is equivalent to something in the second set, and vice versa. They must be the same set. Chapter 2, in order to show that 2 sets were equal, we showed that they were subsets of one another. Page 643, Theorem 1. In order for me to prove this, I would have to prove from 1 to 2, from 2 to 3, and then from 3 to 1. We did case proofs just like this back in chapter 1, section 8. A question for you. Sticking with our example of looking at remainders mod 7, the mod 7 relation we were just looking at, we said there were a total of 7 classes. Every integer possible must fall into one of those classes. And the classes have no overlap, which means every single integer is spoken for. I can take that entire infinite set, positive and negative integers, and column them up so that all the ones with the remainder 0, all the ones with the remainder 1, 2, 3, 4, 5, 6 are aligned. And nothing is missing. Undergraduate students. I can take every undergraduate student on this campus and ask which of the 4 classes they are in. How many credits do they have? And then I know whether they're a freshman, a sophomore, a junior, or a senior, right? If I have a set, I can form a partition of a set by creating a bunch of subsets that follow the following rules. None of the subsets are empty. The subsets have no overlap. And when you put them all together, you get the whole set. What we just built with our equivalence classes is a partition of the integers. These are the equivalence classes we were just talking about. The things whose remainder when you divide by 7 is 0, 1, 2, 3, 4, 5, and 6. None of the integers are missing from this list. And none of these sets have any overlap. And when I put them all together, I get all of the integers. And none of them are empty. Check, check, check. Students, when you got here, if you came in as a traditional undergraduate for welcome weekend, that first weekend on campus, they took you all out of McKenna at the end of the day. Your parents left as you were moving into the dorms. They took a picture, right? Took you out on the lawn and took a picture of everybody. I think even that weekend they gave you all shirts and they said you could wear the matching shirts for that weekend. We have a picture from 4 years ago, 3 years ago, 2 years ago, 1 year ago, this year. I can tell you how many credits should be in each of those pictures, shouldn't I? If people are on track with their degrees, those pictures are these classes, aren't they? And that's the entire undergraduate body. In one of those 4 groups, there's no overlap between the groups. None of the groups are empty, and that's the whole undergraduate body. Now, if you're a transfer, you're not in one of those pictures, I'm sorry, we'll take your picture at commencement. If you're a non-traditional student, we'll take your picture at commencement. We'll get you in one of them anyway. Equivalence relations make partitions. I don't know how many of you do crossword puzzles, but there is an entire dictionary of crossword puzzle words sorted by length. Wasn't that our opening equivalence relation? Two things are equivalent when they have the same length. Every possible string of English letters has some length. I don't care if you're looking at one of those giant $20 words. It's still some finite number of letters. Even if it's this word with no letters in it. That's got a length of 0. That's still an equivalence class. But then the rest of the words in the English language can be divided up by how long they are. And that's a partition of strings of letters. It works the other way too. I'm going to write down a set. I want you to chop this set up into a couple of pieces. Let's do 3 pieces. I want you to chop this set up into 3 pieces. I don't care what those 3 pieces are. What 3 pieces are you going to pick? Go for it.
1, 5, 2, and 4, 3, and 7.
So I'm going to call this set 1, this set 2, and this set 3. This is a partition. None of those sets are empty. They don't have any overlap. And when I put them all together, I get the whole set, right? That's a partition. It's created an equivalence relation. There's a list of all the ordered pairs of things that are in this relationship. A and B are related if they're in the same subset. So 1 is related to 1, 1 is related to 5. 5 is related to 1, and 5 is related to 5. And so on for all of the sets that you gave me, Gavin. Is this reflexive? It's reflexive if I see AA for every one of the elements. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Check. If you see AB, you also see BA for every possible pair. Triangles is the hard one, right? I should make a matrix and do that Boolean product thing. Or maybe I should draw the picture and see about looking for triangles. But now that I have the relation, I can verify this is transitive. That means that this relation, that all we did was we made it up by chopping up this set. This made an equivalence relation. Equivalence relations are the foundational idea behind more abstract mathematics, more abstract programming. This is classes. This is object-oriented programming. Love to tell you this is useless. You're never going to use it anywhere. So many places. In 3 of the other books I have right here with me for other classes, one of the opening chapters, every one of them is about equivalence relations. And they are the foundation of how we move forward in those classes. That is why it is the last topic we do here, so that you will get to see it in all of those other places. I will see you on Monday, where you will turn in all of your final homeworks, and we will answer any questions you have about the exam. I hope you all have a wonderful weekend. If you came in late and you have a homework assignment for me, come get it.